The Power of Machine Learning in Data Science. Welcome to the Data Futures podcast. I'm your host, Daniel Parente, here to discuss how machine learning is transforming data science capabilities compared to traditional analytics. Across industries from transportation to healthcare, companies now record vast data sets, capturing in fine detail aspects of operations, customers, and markets. Turning colossal data pools into meaningful insights presents a huge challenge. This is where data scientists come in, and machine learning has become their most powerful tool. Machine learning represents a branch of artificial intelligence, allowing software applications to essentially improve and optimize themselves by learning patterns within input data, rather than solely executing predefined logic coded by developers. The unique attributes of machine learning algorithms grant them analytical superpowers unmatched by previous generations of software. Once trained on sample datasets, machine learning models can automate complex tasks, process massive data volumes, rapidly enhance predictive accuracy, and adapt to fluctuating real-world conditions. These capabilities make machine learning the driving force taking data science into the future. Let's explore some key machine learning advantages over traditional analytics. First, machine learning delivers automation of intricate tasks, defeating traditional coding. By writing their own adaptive software instructions, instead of just rigidly following rules written by humans, machine learning models can take over intricate responsibilities previously requiring data scientists' manual effort. For instance, an image recognition tool based on machine learning can automatically label new pictures presented to it without needing human verification after each identification. Contrast this to a traditional programmed computer vision tool only capable of making decisions based on the specific images it was originally shown by developers. The machine learning application compounds its knowledge. Another example is predictive customer lifetime value models. Rather than data analysts trying to manually parse millions of customer transaction records to identify common purchase patterns, an ML model can digest the data to automatically uncover hidden insights at enormous scale. This automation of complex analytical workflows lets data teams shift their focus to higher-level responsibilities, like translating model outputs into business recommendations. Machine learning massively amplifies the speed and scale of data science. A second advantage is machine learning's proven effectiveness at processing massive datasets traditional techniques fail to handle. Most analytical methods reach their limits once data volume passes a certain threshold. But machine learning actually thrives when ingesting billions of data points. The models can discern subtle patterns across immense data pools, which human analysts have no hope of fully examining manually. Machine learning can now demonstrate its capabilities thanks to access to large amounts of data. This was not possible when models were trained on small samples. Machine learning helps enterprises translate once useless data overflow into strategic advantage by detecting overlooked efficiency gains and growth opportunities. UPS provides a real-world demonstration, leveraging machine learning across a staggering 16.5 petabytes of historical routing data. By uncovering granular shipping demand patterns within massive data stores, UPS optimizes daily routes and inventory flow. This yields hundreds of millions in cost savings while improving customer service through machine insights unseen via conventional analytics. The third major machine learning advantage is rapidly compounding model accuracy over time. Machine learning models improve over time by learning from new data, making predictions and decisions more accurate through self-correction. Let's say a machine learning model created to predict subscription retention rates starts with decent 75% accuracy. After processing more customer records in its first month, the model improves to 82% accuracy without any changes to its algorithms. This means machine learning models compound knowledge versus analytical models produced through traditional programming or statistical methods, which deliver static results fixed at the point of creation. Continual learning curves set machine learning apart. The fourth advantage is adaptability to fluctuating real-world conditions. Unlike traditional analytical models that assume stable environments, machine learning applications have the ability to automatically detect and incorporate signals that indicate changes in external factors, which greatly impact the accuracy of the models. This makes them resilient against unpredictable data shifts that would lead traditional models astray. For example, during an economic downturn, a forecasting algorithm might fail to predict warning signs of a recession. As a result, revenue could be lost due to overstocking before the algorithm realizes the situation. A machine learning model would automatically perceive rising anomalies in purchasing data as leading indicators to tweak its logic, avoiding costly assumption errors. Research shows machine learning adjusting sales projections, medical diagnoses, weather forecasts, and much more by detecting data deviations and updating its heuristic rules to compensate. This built-in adaptability offers organizations navigation resilience through growing volatility across markets, supply chains, and more. So in review, we discussed 4 differentiators establishing machine learning's pole position over previous analytics methods. First, automating intricate analytical tasks to greatly accelerate data science productivity. Second, effectively handling massive real-world datasets that cause traditional methods to choke. Third, rapid accuracy improvements via constant self-optimization as new data gets processed. And fourth, automated adaptability to changing conditions evident in data streams. These differentiators make machine learning an indispensable tool for data science teams tasked with extracting insights from ever-growing, ever-changing mountains of enterprise data. Of course, we must balance the strengths of machine learning with awareness around limitations. First, machine learning models usually require vast datasets to demonstrate their full potential. Organizations lacking big data scale will hit limitations. Second, machine learning unfortunately suffers from a major explainability problem. Even experts often cannot clearly understand why models generate specific outputs. Lacking transparency prevents more widespread adoption across industries like healthcare, where explainability is mandatory. Lastly, machine learning can unintentionally perpetuate harmful biases if their training data incorporates distorted demographic samples, short-sighted assumptions, or stereotyped labeling. Users have to carefully monitor model behavior to prevent encoding unfairness. So in closing, by combining machine learning together with responsible data science practices, leading organizations now make the most of exponentially growing data resources to drive unprecedented innovation. Proper understanding of both profound opportunities and ethical obligations will determine who best harnesses machine intelligence. I hope this episode has illuminated machine learning's analytical superpowers, elevating data science and the enterprises willing to embrace them. Thanks for listening.